Section 1.6, Cloud-Native Topologies. My explanation of cloud-native didn't involve specific technologies or architectures. The CNCF mentions some in its definition, like containers and microservices, but those are just examples. You don't have to use Docker containers for your applications to be cloud-native. Think about serverless or PaaS solutions. Writing functions for the AWS Lambda platform or deploying applications to Heroku doesn't require you to build containers. Still, they are categorized as cloud-native. In this section, I'll describe some common cloud-native topologies. See Figure 1.9. First, I'll introduce the concepts of containers and orchestration, which will be further explored later when I discuss Docker and Kubernetes. Then I'll present the topic of serverless technologies and functions, FaaS. I will not focus much on the FaaS model in this book, but I will cover the basics of how to build serverless applications using Spring Native and Spring Cloud Function.
Figure 1.9. The main cloud-native computing models are containers, managed by orchestrators, and serverless.
Section 1.6.1, Containers. Imagine you join a team and start working on an application. The first thing you do is follow a guide to set up your local development environment that's similar to the ones used by your colleagues. You develop a new feature and then test it in a quality assurance, QA, environment. Once it's verified, the application can be deployed to staging for some extra testing and finally to production. The application is built to run in an environment with specific characteristics, so it's essential to have all the different environments as similar as possible. How would you do that? That's where containers enter the scene. Before containers, you would rely on virtual machines to guarantee the reproducibility of the environment, isolation, and configurability. Virtualization works by leveraging a hypervisor component that abstracts the hardware, making it possible to run multiple operating systems on the same machine in an isolated fashion. The hypervisor would run directly on the machine hardware, Type 1, or on the host operating system, Type 2. On the other hand, an OS container is a lightweight executable package that includes everything needed to run the application. Containers share the same kernel as the host. There's no need to bootstrap full operating systems to add new isolated contexts. On Linux, that is possible by leveraging a couple of features offered by the Linux kernel. Namespaces for partitioning resources among processes so that each process, or group of processes, can only see a subset of the resources available on the machine. C groups for controlling and limiting the resource usage for a process, or group of processes. Note: when using virtualization only, the hardware is shared, whereas containers also share the same operating system kernel. Both provide computing environments for running software in isolation, even if the degree of isolation is not the same. Figure 1.10 shows the difference between virtualization and container technologies.
Figure 1.10. Virtualization and container technologies differ in what is shared across isolated contexts. Virtual machines share the hardware only. Containers share the operating system kernel as well. Containers are more lightweight and portable.
Why are containers so popular for cloud-native applications? Traditionally, you would have to install and maintain the Java Runtime Environment, JRE, and middleware on a virtual machine to make your application run. Instead, a container can run reliably in almost any computing environment, independent of the application, its dependencies, or middleware. It doesn't matter which kind of application it is, in which language it's written, or which libraries it uses. All containers have a similar shape from the outside, just like the containers used for shipping. Therefore, containers enable agility, portability across different environments, and deployment repeatability. Being lightweight and less resource demanding, they are perfect for running in the cloud, where applications are disposable and scaled dynamically and quickly. In comparison, building and destroying virtual machines is much more expensive and time-consuming. Containers! Containers everywhere! Container is one of those words that can mean different things. Sometimes this ambiguity can generate confusion, so let's see what it means in specific contexts. An OS container is a method for running one or more processes in an environment isolated from the rest of the system. This book will focus on Linux containers, but note that Windows containers also exist. Docker. A Docker container is an implementation of a Linux container. OCI. An OCI container is a standardization of the Docker container implementation by the Open Container Initiative, OCI. Spring. A Spring container is the application context where objects, properties, and other application resources are managed and executed. Servlet. A servlet container provides a runtime for web applications leveraging the Java Servlet API. The Catalina component from the Tomcat server is an example of a servlet container. Virtualization and containers are not mutually exclusive. You can use them both in a cloud-native context, having an infrastructure made up of virtual machines on which you run containers. The infrastructure as a service, IaaS model, provides a virtualization layer that you can use to bootstrap new virtual machines. On top of that, you can install a container runtime and run your containers. An application is usually made up of different containers that can be run on the same machine during development or while performing early testing. But you would quickly reach the point where it gets too complicated to manage many containers, primarily when you start replicating them for scalability and distributing them across different machines. That's when you'll start relying on the higher level of abstraction provided by the Container as a Service, CaaS, model, which offers functionality to deploy and manage containers in clusters of machines. Note that, behind the scenes, there is still a virtualization layer. Containers are involved even when you're using PaaS platforms like Heroku or Cloud Foundry. You deploy your applications on those platforms by providing just the jar artifact, since they take care of the JRE, the middleware, the OS, and any needed dependencies. Behind the scenes, they build a container out of all those components and finally run it. The difference is that it's no longer you who is responsible for building a container, the platform does it for you. On the one hand, that's convenient, in terms of fewer responsibilities for developers. On the other hand, you are giving up control over the runtime and middleware, and you might face vendor lock-in. In this book, you'll learn how to use cloud-native build packs, a CNCF project, to containerize Spring applications, and you'll use Docker to run them in your local environment. Section 1.6.2, Orchestration. So you have decided to use containers, great. You can rely on their portability to deploy them to any infrastructure providing a container runtime. You can achieve reproducibility, so there are no bad surprises when moving containers from development to staging to production. You can scale them quickly, since they're so lightweight, and get high availability for your applications. You're ready to adopt them for your next cloud-native system, or are you? Provisioning and managing containers on a single machine is pretty straightforward. But when you start dealing with tens or hundreds of containers scaled and deployed on several machines, you need something else. When you move from virtual servers, the IaaS model, to container clusters, the CaaS model, you're also switching your point of view. In IaaS, you focus on single computing nodes, which are virtual servers. In CaaS, the underlying infrastructure is abstracted, and you're focusing on clusters of nodes. With the new perspective offered by CaaS solutions, the deployment target will not be a machine anymore, but rather a cluster of machines. CaaS platforms, such as those based on Kubernetes, provide many features to address all the significant concerns we look for in a cloud-native environment, orchestrating containers across machines. The two different topologies are shown in Figure 1.11.
Figure 1.11. The deployment target of containers is a machine, whereas for orchestrators, it's a cluster.
Container orchestration helps you automate many different tasks. Managing clusters, bringing up and down machines when necessary. Scheduling and deploying containers within a cluster to a machine that meets the container requirements for CPU and memory. Dynamically scaling containers for high availability and resilience, leveraging health monitoring. Setting up networks for containers to communicate with each other, defining routing, service discovery, and load balancing. Exposing services to the internet, establishing ports and networks. Allocating resources to containers according to specific criteria. Configuring the applications running within the containers. Ensuring security and enforcing access control policies. Orchestration tools are instructed declaratively, such as through YAML files. Following the format and language defined by the specific tool, you usually describe the state you'd like to achieve. For example, You would like to have 3 replicas of your web application container deployed in a cluster, exposing its services to the Internet. Examples of container orchestrators are Kubernetes, a CNCF project, Docker Swarm, and Apache Mesos. In this book, you'll learn how to use Kubernetes to orchestrate the containers for your Spring applications. Section 1.6.3, Serverless. After moving from virtual machines to containers, we can abstract the infrastructure even more. That's where serverless technologies are placed. The serverless computing model enables developers to focus on implementing the business logic for their applications. The name serverless might be misleading. Of course there is a server. The difference is that you do not need to manage it or orchestrate the application's deployment on it. That's a platform responsibility now. When you use an orchestrator like Kubernetes, you must still consider infrastructure provisioning, capacity planning, and scaling. In contrast, a serverless platform takes care of setting up the underlying infrastructure needed by the applications, including virtual machines, containers, and dynamic scaling. Serverless architectures are usually associated with functions, but they comprise 2 main models that are often used together. Backend as a service, BaaS. In this model, applications rely heavily on third-party services offered by cloud providers, such as databases, authentication services, and message queues. The focus is on reducing development and operational costs related to back-end services. Developers can implement front-end applications, such as single-page applications or mobile applications, while offloading most or all of the back-end functionality to BaaS vendors. For example, they could use Okta to authenticate users, Google Firebase for persisting data, and Amazon API Gateway to publish and manage REST APIs. Function as a service, FaaS. In this model, applications are stateless, triggered by events, and fully managed by the platform. The focus is on reducing deployment and operations costs related to orchestrating and scaling applications. Developers can implement the business logic for their applications, and the platform takes care of the rest. Serverless applications don't have to be implemented with functions to be categorized as such. There are 2 main FaaS offerings. One option is to go with vendor-specific FaaS platforms, such as AWS Lambda, Azure Functions, or Google Cloud Functions. Another option is to choose a serverless platform based on open-source projects, which can run either in a public cloud or on premises, addressing concerns like vendor lock-in and lack of control. Examples of such projects are Native and Apache OpenWhisk. Native provides a serverless runtime environment on top of Kubernetes, as you'll see in Chapter 16. It's used as the foundation for enterprise serverless platforms like VMware Tanzu Application Platform, Red Hat OpenShift Serverless, and Google Cloud Run. Serverless applications are typically event-driven and run only when there is an event to handle, such as an HTTP request or a message. The event can be external or be produced by another function. For example, a function might be triggered whenever a message is added to a queue, process it, and then exit the execution. When there is nothing to process, the serverless platform shuts down all the resources involved with the function, so you can really pay for the actual usage. In the other cloud-native topologies like CaaS or PaaS, there is always a server running 24/7. Compared to traditional systems, they offer the advantage of dynamic scalability, reducing the number of resources provisioned at any given time. Still, there is always something up and running, and it has a cost. In the serverless model, resources are provisioned only when necessary. If there is nothing to process, everything is shut down. That's what we call scaling to zero, and it's one of the main features offered by serverless platforms. Besides cost optimization, serverless technologies also move some extra responsibility from the application to the platform. That might be an advantage, since it allows developers to focus exclusively on the business logic. But it's also essential to consider what degree of control you would like to have and how you will deal with vendor lock-in. Each FaaS, and in general serverless platform, has its own features and APIs. Once you start writing functions for a specific platform, you can't move them easily to another, as you would do with containers. With FaaS, you might compromise more than with any other approach, prioritizing responsibility and scope at the cost of control and portability. That's why Native became popular quickly. It is built on Kubernetes, which means that you can easily move your serverless workloads between platforms and vendors. In the end, it's a matter of trade-offs.